This Zoom session is being brought to you by the Fractal Snowpoint. All right, for today, we're going to be doing geometric series, finite, infinite, and finite and infinite geometric sum sequences. Sequences and series. A sequence is like it's an infinite list, and it goes like this. It starts with a first term a, and each next term is bigger by a factor of r. So it's a, ar squared, ar cubed, and so on. R is the common ratio. A is the first term. The nth term is a times r to the n minus 1. The n minus 1 is so we can have so the a1 will be will just be a. You see. So for example, a n is 2 times 3 to the n. The common ratio is 3. The first three terms are 6, 18, 54, 162, 486, and so on, going on forever like that. Sometimes they started a0. Well, so that would be the 0th term, whatever. Okay, a geometric series is a sum, a partial sum of a geometric sequence. Summation from 1 up to n ar to the k minus 1. So it goes a plus ar plus ar squared all the way up to ar to the n minus 1. So then if Sn is that, then if you multiply by r, that shifts every term over by 1. A becomes ar becomes ar squared becomes ar to the third, and so on. Ar to the n minus 2 becomes ar to the n minus 1, and ar to the n minus 1 becomes ar to the n. So multiplying by r basically shifts the sequence, the series, over one term. But that means that all these middle terms are identical, and we can eliminate them by simply subtracting. So we take Sn minus Rsn, a survives, all these terms in the middle go away, and we're left with minus ar to the n. So the middle terms cancel out. Sn times Rsn equals a minus ar to the n. Okay, then we do some factoring. Pull out an Sn, 1 minus Rsn equals, pull out an a times 1 minus r to the n. Then dividing it, Sn equals a times 1 minus r to the n over 1 minus r. This is the sum of a geometric series. So for example, 1 plus 3 plus 9 up to 2187. Okay, the initial term is 1, the common ratio is 3, and you can figure out that there's 8 terms. So the sum is 1, is a times 1 minus r to the n over 1 minus r, therefore 1 times 1 minus 3 to the 8 over 1 minus 3, which after a little bit of figuring is 3,280. Here's 1 minus 2 plus 4 minus 8 plus 6 minus 32, all the way alternating up to minus 2048. Okay, the initial term is 1. The common ratio is negative 2, and you can figure out that there are 12 terms here. So therefore, the sum is 1a times 1 minus r to the n over 1 minus r. So 1 minus 12, negative 2 to the 12th over 1 minus negative 2. And after some figuring, it's negative 1,365. Now, if we let the series go on forever, that's called an infinite geometric series. 1 plus ar squared plus ar cubed, and so on. Now, if we go back to this initial term, this initial sum, what is that going to be? Well, it depends upon how this behaves when n approaches infinity. And that in turn depends on the size of r. If r has absolute value bigger than 1, then this blows up. It becomes ever larger, or sometimes alternating, ever positive, ever large positive, and ever bigger and bigger. And so it diverges, so-called, and there is no limit. So it doesn't make sense. Whereas if it's and if it equals exactly 1, then it's a plus a plus a plus a plus a plus a, which goes up to infinity times a. Or if it's negative 1, a minus a plus a minus a plus a minus a, which alternates between 0 and twice and 0 and a. So that also fails to reach a limit. But if r is absolute value less than 1, then r to the n approaches 0. It vanishes, and we're left with a, and this becomes 1 over 1 minus r times a, and the series converges to a over 1 minus r. That's the limit of an infinite geometric series, a over 1 minus r. So, for example, 1 plus a third plus a ninth plus etc. Well, The initial term is 1, so put that here, 1 over. The common ratio is 1/3, so 1 over 1 minus a third, which is 1 over 2/3, is 3/2. Here, it's 1 minus third plus a 9 minus 1/27, and so on. Here, the initial term is 1. The common ratio is negative 1/3, so it's 1 over 1 minus negative a third. That's 1 over 4/3, which is 3/4. Here we have 1 plus 3/2 plus 3/2 squared plus etc. Well, this 3/2, common ratio of 3/2 is bigger than 1, so it diverges. Here's 3 plus 3 times 1 plus 1 plus 3 times 1 plus 1 squared, etc. Common ratio is 1.1, bigger than 1, so this too diverges. But suppose it's 3 plus 3 times 0.9 plus 3 times 0.9 squared, etc. Well, the initial term is 3. Common ratio is 0.9. So 3 over 1 minus 0.9, which is 3 over 0.1, which is 30. Now here, we can, here we have a repeating decimal, 0.523232323. The question is to write that as a fraction of integers. All right. Well, okay, we can do that by using a geometric series. First, we break it into the non-repeating part, 0.5, and the repeating part, 0.02323232323, etc. Okay, 0.5 will just keep, it's 5/10. 0.023 is 23232 is 0.023 times 1, 0.01, 0.01, 01, 01. This 01 basically shifts this thing over 2 places. We do so repeatedly. Okay, now this 1.01010101 and so on, you can think of as an infinite series, infinite geometric series. It's 1 plus 0.01 to the first, plus 0.01 to the second, plus 0.01 to the third, etc. forever. So we'll write that as the initial term 1 over the 1 minus the common ratio, 0.01. So we have 0.05 plus 0.023 over 1 minus 0.01. Okay, so this is 5/10 plus 23 over 1,000 of 1 over 0.99. And this is 99 over 100. This is 100 over 99. Bit of integer of fraction arithmetic gives you 5/10 plus 23 over 990. And a little bit more fraction arithmetic gives you 259 over 495. So you can, so any repeating decimal can, by this means, be considered as including a geometric series, and thus can be written as a ratio of integers. And conversely, any ratio of integers turns out to be a repeating decimal. So the two are the same. Okay, I think that's it. That's for the section for now.